In this lesson, we're going to look at the final two methods for factoring. So we've learned four methods thus far. We've learned how to factor any number polynomial using the GCF method, the greatest common factor. Then we learned the grouping method, which works for four-term polynomials or anything larger than four terms in even increments. Then we learned the trinomials without a coefficient method and the trinomials with coefficients methods. So today we're going to finish out those six methods by learning perfect square trinomials and difference of squares and how to factor these final two methods. So before we get into the actual methods, let's review how we would simplify a binomial squared, because this will relate to how we'll factor perfect square trinomials. And this is the third kind of trinomial method. So after you learn this method, it will be up to you to determine which method for trinomials is most appropriate. So here we have 2x minus 5 squared, which really, the squared, remember, means to write your base out twice, so multiplied by itself 2 times. And so when we write that out, we'll do 2x times 2x, which is 4x squared, 2x times negative 5 times 2x, and negative 5 times negative 5. So after all of that multiplication, we should get 4x squared minus 10x plus 25. And this minus 10x portion repeating is not a coincidence, because we are multiplying the same two terms to get those 10x's, whether it be a 2x and a negative 5 or a negative 5 and a 2x. That's not a coincidence right there that it happens, but that will simplify to a middle term of negative 20x. So we, in our monomials and polynomials unit, looked at a shortcut for multiplying out binomial squares, where we talked about it should expand out, where the first term is made from just taking the first term in the binomial and squaring it. So 2x squared is 4x squared. Then taking the second term in the binomial and squaring that to a 25. So negative 5 times negative 5 is 25. Then for the middle term, and this was the part that was a little bit different, we take the two terms, 2x and negative 5, and we multiply them together to get that negative 10x. And because it will show up twice, we double this negative 10x to get negative 20x, which ends up being your middle term. So that was the shortcut that we used. And again, last unit, you could have stretched it out. You didn't have to use the shortcut, but it certainly was helpful in recognizing that pattern. So today we're going to learn how, when we end up with a trinomial like this, 4x squared minus 20x plus 25, that this is a special kind of trinomial. So this is called a perfect square trinomial. So trinomials are perfect squares when the first and last term are perfect squares, and the middle term is twice the product of the square roots of the first and last term. So here we had, you can see the first term is a perfect square, 4x squared, I could take the square root of it. Positive 25 is a perfect square, I could take the square root of it. And the middle term would be twice the product of the square root. So let's break down what that looks like. So here's yet another example of a perfect square trinomial. You can see that the first term and the last term are perfect squares. Notice I'm circling the positive sign with this 16. It should be a positive to be able to take the square root of it. So the first and last terms are perfect squares. That means I can take the square root of 9x squared to get 3x, and I can cleanly take the square root of 16 to get 4. Once I've done this, to verify if this is in fact a perfect square trinomial, we do need to meet one other rule. So we've met the first rule that the ends are perfect squares. The second, though, is to make sure that the middle term is twice the product of the square roots of the ends. So I take 3x and 4 and I multiply them together. So 3x times 4, and usually you'll do this in your head, but that is 12x. Lastly, double this to get 24x. It is positive, and just ensure that that middle term, in fact, is twice the product of the square roots of the ends. And so in this case, both check out. So this is an example of a perfect square trinomial. So if and when you recognize that a trinomial is a perfect square trinomial, this will be really convenient for you because we will be able to factor it quite easily. So if you see that the trinomial is a perfect square trinomial, you can write the binomials of the roots squared. So it's a very quick factor. All you have to do is take the square roots of your ends. So we get square root of 9x squared to be 3x, square root of 16 to be 4. And all you do is put 3x and 4 in a binomial. And whatever the middle term sign is, you bring it down and put that in between the square roots of your ends and square your binomial. So the sign in the middle always stays the same as whatever the middle term sign was in the original trinomial. And here we factored. Now the thing with perfect square trinomials is you can use the trinomial with a coefficient method to factor this. This is a shortcut that we're learning today. You could certainly do 9 times 16, find factors of that add up to 24, so 144, and then break it apart, finish by grouping, and follow that much longer method. However, if you recognize that this is a perfect square trinomial, then it's going to be really quick and easy to write its factored out form. So you can express this as 3x plus 4 squared, which is the same as 3x plus 4 times 3x plus 4. Either of these answers would be correct for how you factor this out. So just to recap just a little bit, let's go ahead and take a look at these trinomials and just see, are they perfect square trinomials? Because half of the battle with this is just determining when you actually have a perfect square trinomial. So the way we'll test this is see if we take the square roots of our ends, or can we? And in this case we can. Square root of 25a squared is 5a, and square root of 9 is 3, so that works out. And then we want our middle term to be twice the product of the square roots of the ends. So 5a times 3 together make a 15a, and if we double it, we get 30a. So this is a perfect square trinomial. Let's take a look at the next one. Here we have the square root of 4x squared, which can be taken, and the square root of positive 16, which can be taken. So this one would give us a 2x, and this would give us an 8. Now we want to confirm, oh, not an 8, I'm sorry. Talking and writing. Okay, which would give us a 4. Now we want to confirm that the middle term would be double the product of the ends square roots. So 2x times 4 is 8x. And if we double that, that's 16x. Now, regardless of this sign in the middle, this should be a 16 for this to, in fact, be a perfect square trinomial. Because the middle term is not, then this is not a perfect square trinomial. Now, I do want to emphasize that that does not mean this cannot be factored. Hopefully, you can see right away there is a GCF, and it could potentially factor further after that GCF is pulled out. But all that we're doing here is confirming whether or not that shortcut would be able to be used. All right, let's take a look at our next one. If I take the square root of my ends, it is possible. The square root of 36b to the 4th would be a 6b squared. Remember to have your exponent when you're square rooting it. And the square root of y squared is y. Now, we want to confirm that our middle term would be twice this product. So 6b squared times y doubled would be a 12. So if I double this, it's going to be a 12b squared y. And that is, in fact, what we have. This middle term sign can be negative, so that's fine. So this is a perfect square trinomial, and you would be able to use the shortcut method to factor it. Lastly, you can see 49x squared is a perfect square we can take the square root of. And while 4 is a perfect square, it's negative. we cannot take the square root of a negative. So right away, we cannot factor this as a perfect square trinomial with the shortcut. So with that one, you would have to look for your trinomial with a coefficient method. And if none of those things can happen, then you would just say it's prime. But we do know we would not be able to use our shortcut for that one because this of the last term being negative. So just to recap, always check your middle terms to make sure that the middle term is double the product of the square roots of the ends, and that this last term must be positive for us to take the square root of it. Okay, so let's just practice a little further. We did already confirm that the first example, 25a squared plus 30a plus 9, it's right here, is a perfect square trinomial. So now that we have confirmed it's a perfect square trinomial, then to factor it, take the square roots of your ends. So this is 3, and this is 5a. And then all you do is take your 5a and your 3, and those become the parts of your binomial. Whatever the middle term sign is, that's what goes in between. Do not forget this is squared. That's that binomial squared. And to practice once again this method, we confirm this one is a perfect square trinomial already as well. So let's factor it with our shortcut method. So take the square roots of the ends. 36b to the fourth, the square root of it was 6b squared. The square root of y squared is y. Those pieces go into your binomial, and whatever the middle term sign is, that's negative. And if ever you're not sure, go ahead, stretch it out, and make sure that if you were to multiply back through, that you would get the same thing. So, sorry for this black mark here, but this gives us 36b to the fourth minus a 6b squared y minus another 6b squared y, and a plus, negative times negative is positive, y squared. And negative 6b squared y minus 6b squared y will combine to be the negative 12b squared y that we're looking for in the middle. So you can see that this actually does work out. So this is our answer. Okay, so that is our perfect square trinomial method that we can use. Like I said, with these, you by all means can take the longer trinomial methods for factoring and factor using the factors of the final term that have the sum of the middles, or the trinomial with coefficients methods. And either of those would work on this one because of our 1y to the squared, or just your trinomial with a coefficient method would work here as well. Like I said, it's just a lot more work, and if you can recognize the shortcut, it sure will save you time. All right, so that was our fifth method of factoring. It was perfect square trinomials. Now we're going to look at our final sixth factoring method. So just to recap, like we did with the trinomials, let's review what a binomial scenario like this would multiply out to. So here we have two nearly identical binomials, but their signs are different. So if you'll recall, when we multiply something like this out, the middle term situation is interesting because 3x times 3x is a 9x squared. Then 3x times 2 is a positive 6x. A negative 2 times 3x is a negative 6x, and a negative 2 times positive 2 is a negative 4. Well, what happens in this case, which is slightly different from what we just saw when it was a binomial squared, is the signs of the middle terms are actually opposites, which means that when we add them or combine those like terms, they become 0x, meaning that they go away. And all we're left with are the 9x squared and the minus 4. So what this is called is a difference of squares. And you can see that our shortcut to multiply this out when we recognize this was to always square the first term, the first binomial part. 3x squared gives us the 9x squared. Square the second binomial part, or the last binomial part, to get the 4. So there's our 9x squared and our 4, and we always put a subtraction sign in the middle because this is created by two binomials that have their signs as opposites as the last term. So a negative times a positive would always be a negative. So that was the shortcut for multiplying something out like this. So today we're going to now go backwards from a binomial like this and factoring it out to those two original binomials you're seeing. So this is called a difference of squares binomial. So this piece right here, 9x squared minus 4, is a difference of squares. And it gets that name because we are taking the difference, subtracting, two perfect squares, 9x squared and 4. Now here you ignore the subtraction sign. So we can take the square root of 4 and we can take the square root of 9x squared. So a binomial is the difference of two squares if the first and last term are perfect squares and the sign in the middle is subtraction. Now this one, for this method, you are going to just have to memorize how this is done once you recognize that a difference of squares is there. So here we have x squared minus 36. This is a binomial, and this is the only kind of binomial that will factor out other than being able to pull a GCF out of it. So here I can see the first term is a perfect square, the second term is a perfect square, and the middle sign is subtraction. So this is a difference of squares, and if you recognize that, then to factor it, we will take the square, oh, and I might have this on the next slide. Yes, here it is. Okay. Sorry, so this was just as I just spoke through, confirming that this is a difference of squares. So we've got all the correct parts there. So if you recognize your binomial is a difference of squares, then you can immediately write the answer as two identical binomials with opposite signs, one positive, one negative. So the way we'll do this is square root both perfect squares. So the square root of x squared is x. The square root of 36 is 6. X and 6 will make up the parts of your binomials in your answers, and in between them, one of them gets a plus sign, the other gets a subtraction. So if you wanted to check this back out, you could re-multiply just to confirm that it will in fact simplify. And these are negative and positive, they'll cancel out, and we do get back to x squared minus 36. So this is the factored out version of x squared minus 36. So just to recap, if we're looking at these examples to confirm whether one would be factorable as difference of squares or not, here in our first example, we've got a perfect square here at the front. I can take the square root of it. And the last term is a perfect square as well, and there is subtraction in between. So this is a difference of squares. In the next example, our two parts are both perfect squares. However, the sign in the middle is positive. Therefore, it is not a difference of squares. And if you can't pull a GCF out of that binomial, then this one couldn't be factored at all, and this one's actually prime. Now, that means that just because it's got a plus sign here does not mean it's always going to be prime. Sometimes there is a GCF that can come out of the two terms. In this case, there is no GCF and it's not a difference of squares, so it would be prime. Looking at our next example, 9x squared is a perfect square. The square root of it's 3x. 49 is a perfect square. We do have subtraction in the middle, so this is a difference of squares. And lastly, 64b to the 6th, we could take the square root of. It's got an even exponent, so we're good there. 25a squared, we can also take the square root of, and we've got subtraction. So another difference of squares. Let's practice factoring those now that we've identified which ones can be factored as difference of squares. So the method is we take the square roots of the parts, and those pieces, so square root of x squared is x, square root of 4 is 2. Those pieces make up the parts of your binomials. One binomial gets a plus sign and the other gets a minus. It doesn't matter which one's which. For our next example, square root the perfect squares. So square root of 9x squared is 3x. Square root of 49 is 7. 3x and 7 make up the pieces of your binomials. One gets plus, one gets minus. And the last example, to take the square root of 64b to the 6th. The square root of 64 is 8. The square root of b to the 6th is b to the 3rd. You just take half the exponent. Square root of 25a squared is 5a. Hard to write with this pen. Oh, yep. Okay, and those make up your two parts of your binomials. One gets plus, one gets minus, and we are fully factored. Want to take a look at one last example that has fractions in it. Remember, you can take the square root of fractions, so let's see if this is in fact a difference of squared. You can see the variables have even exponents, so we can take the square root of them. Remember, to take the square root of a fraction, you can square root your top, square root your bottom to get 3/4 in that case. Here, I can square root the top, square root the bottom to get 2/5. So both fractions are perfect squares as well. So this actually is a difference of squares. So if it is, you just follow your same process, square root the first term, square root the second. And in your final binomials, one gets a plus sign, one gets a minus. So this can factor as well. So don't freak out if you see fractions. We can take the square roots of those too. And that is all for our lesson today.